Hello friends, it's great to see you on our channel. Today we have a lot of interesting things to discuss, and I hope you're ready to dive in. Let's make our journey a fascinating one. Share your thoughts in the comments. We appreciate every perspective on what's happening around us. Today we will talk to you about a very subtle but very serious danger, namely about crazy open, the silent countdown. The universe appears serene. Galaxies drift, stars burn, atoms hum in quiet order. Yet beneath that stillness lies a tension invisible to our eyes, a fragile balance woven into the quantum fields that define reality itself. Within those fields lurks a minute imperfection, a subtle instability experts call metastability. It means our universe may not be in its most stable state, and if that instability gives way, everything we know could transform in an instant. Not speculatively, not metaphorically, mathematically. The odds, 1 in 100. The countdown began long ago. We simply can't hear it ticking. To understand what's at stake, we first have to undo a misconception. In physics, vacuum doesn't mean emptiness. It's the opposite. A churning ocean of fields, particles appearing and vanishing, energy fluctuating perpetually. At every moment, even in the deepest void, something is happening. The so-called vacuum is an active landscape one that gives rise to the structure of everything. Among those fields, one is central to our current understanding of matter, the Higgs field. Discovered indirectly through the Higgs boson in 2012, it permeates all of space. Its average value, the level at which that field rests, determines how elementary particles acquire mass. Electrons, quarks, W and Z bosons each interact with the Higgs field as a swimmer moving through water. The denser that field, the heavier the particle becomes. Without it, atoms wouldn't clump, stars wouldn't shine, chemistry wouldn't exist. The Higgs anchors reality in its present configuration, but a field has potential energy, like a landscape with hills and valleys. The Higgs field happens to reside in a valley that's stable enough to have lasted for 13.8 billion years. Yet calculations of the field's potential derived from the measured Higgs and top quark masses suggest something unsettling. Our valley might not be the deepest one. Somewhere below it, there could be a lower valley, a true vacuum where the field's energy is even less. If that's correct, then the universe is living in a false vacuum, a metastable state that only appears permanent. In ordinary physics, metastability is common. Water can remain liquid below freezing if undisturbed. A supercooled drop sits quietly until a small perturbation triggers crystallization, releasing latent heat as it flips to its true stable form. The same principle applies on the cosmic scale. Our universe might be that drop of water lingering below its freezing point, waiting for the smallest possible disturbance. A perfectly ordinary quantum fluctuation to catalyze a catastrophic phase transition. This idea didn't come from science fiction. It's a mathematical consequence of the Standard Model. When physicists mapped the Higgs potential, they found that for the measured parameters, the curve doesn't settle into the lowest possible energy. There exists a deeper trough beyond an energy barrier, immense but not infinite. Quantum mechanics tells us any barrier, no matter how high, can be tunneled through. With enough time, the field could spontaneously transition from the false vacuum we inhabit to the true one beneath. The probability of that happening at any moment is tiny, but not zero. To truly grasp this, you have to picture the vacuum not as a flat background but as a restless medium. Virtual particles constantly pop in and out of existence, borrowing energy briefly before annihilating back into nothing. The uncertainty principle allows this chaos, ensuring that at quantum scales, emptiness is impossible. Every region of space vibrates with potential. That restless energy defines the cosmological constant, shaping the universe's expansion. Our very existence depends on the delicate interplay between positive matter energy and this pervasive vacuum energy. Now, imagine that underlying vacuum as having multiple configurations, a hierarchy of possible ground states. Each corresponds to different values of fundamental constants, the strength of gravity, the charge of the electron, the mass of quarks. We inhabit just one configuration. The next transition, if it ever occurs, would reset all those parameters simultaneously. Hydrogen might no longer be stable. Atoms could dissolve. Space itself could behave differently. governed by a new set of laws none of our mathematics would survive to describe. This brings us back to metastability, the notion that most natural systems aren't absolutely stable, just stable enough for practical timescales. A diamond is metastable. Given hundreds of millions of years, it's thermodynamically fated to become graphite. But no one worries because the energy barrier is vast. The same reasoning comforted cosmologists. Our cosmic barrier, after all, is unimaginably high. Even if tunneling were theoretically allowed, the expected half-life could exceed 1,030 years orders of magnitude beyond any meaningful concern. Then the calculations improved. New precision measurements of the Higgs boson mass, about 125 GeV combined with refined values for the top quark mass, and the strong coupling constant shifted the parameters slightly. The result placed our universe awkwardly near the boundary between stable and metastable. According to some analyses, we're just inside the metastable region. The standard model alone predicts that our vacuum can decay, given sufficient quantum fluctuation. Suddenly, the barrier didn't look infinite. It looked high but finite. From there, theorists calculated probabilities, the likelihood per unit time per unit volume that a virtual fluctuation could tunnel through the barrier, creating a bubble of true vacuum. Those probabilities depend exponentially on the ratio between the barrier's height and the quantum action required to cross it. Even a small change in the Higgs or top quark mass can swing the figure by many orders of magnitude. But when all uncertainties are folded together, one emerges with a sobering estimate. Within the observable universe and over its current lifetime, the cumulative probability of decay could be on the order of 1%, roughly a 1 in 100 chance that the false vacuum would have collapsed already. The fact that it hasn't might simply mean we're lucky, so far. That may sound alarming, but in cosmic terms, 1 in 100 is not immediate peril. It signifies that statistically, out of 100 universes with parameters identical to ours, perhaps one would have tunneled to its true ground state by now. Yet probability doesn't tell you when the event occurs in any given case. Quantum tunneling has no clock. It's like radioactive decay, completely random. The half-life could be billions of times the current age of the cosmos, or it could happen this instant without violating any law of physics. So, what maintains our apparent stability? Energy barriers and vast scales. The Higgs field's potential barrier may correspond to energies near 10^11 GeV, utterly unreachable by any physical process we can create. Natural fluctuations of that magnitude are extraordinarily rare. Even cosmic events like black hole collisions or gamma-ray bursts lack the local energy concentration to breach it. In short, metastability is secure on human timescales, even geological or galactic ones. But mathematically, the chance remains finite, and in an infinite universe, finite probabilities eventually manifest. Understanding this framework also highlights how precariously balanced physical reality is. Every constant and interaction strength works together to keep the energy density of the vacuum within narrow tolerances. Shift the masses of fundamental particles by even a few percent, and the potential shape changes, perhaps fully stable, perhaps catastrophically unstable. That we sit on this narrow ridge between stability and decay suggests extraordinary fine-tuning, a coincidence physicists still debate. Some invoke the anthropic principle that only universes capable of maintaining long-lived structure will contain observers to question their stability. Others explore deeper symmetries that might lock the vacuum in place more securely than our current equations show. For now, the only empirical fact is that reality has persisted. Returning to the human scale, the concept of a quantum vacuum can seem abstract, but it governs tangible phenomena. The Casimir effect. The tiny attraction between closely spaced metal plates arises directly from vacuum fluctuations. So do Hawking radiation and particle-antiparticle creation near event horizons. These effects confirm that empty space isn't empty at all. It's a dynamic participant in cosmic evolution. Every field contributes to what cosmologists call vacuum energy density, roughly 10 to 9 joules per cubic meter, small but omnipresent. The subtleties of how that energy interacts with gravity determine whether the universe expands forever or collapses. All of this shows that nothingness is, in fact, the most complex something imaginable. The structure of void determines the structure of everything that emerges from it. When physicists speak of vacuum decay, they're really asking whether the foundation of physical law itself is temporary. If the foundation ever shifts, all else follows instantly and absolutely. What's remarkable, and perhaps strangely comforting, is how ordinary this instability is in the grand scheme. Metastability might not be a bug, but a feature a way for the universe to evolve through successive phases of lower energy, each hosting new physics, new structures, perhaps new possibilities. The early cosmos already underwent similar transitions, symmetry breakings that produced fundamental forces and particles. Our current vacuum could simply be one more stage in that unfolding story. This context reframes the 1 in 100 probability not as a countdown to doom, but as a measurement of cosmic imperfection. It tells us the laws of physics are balanced on an exquisite edge, stable enough for galaxies, fragile enough for change. A universe without that tension might be lifeless, static, incapable of producing complexity or consciousness. Maybe metastability is precisely what allowed us to exist long enough to wonder about it. So when we speak of the quantum vacuum, we're not describing the emptiness between things. We're describing the stage on which everything performs. Its subtle jitter is both the origin of creation and potentially the agent of its transformation. Understanding it means recognizing that the calm of the cosmos is not the calm of peace. It's the calm of equilibrium, held by forces so delicate that the smallest fluctuation anywhere, at any moment, could rewrite the script of reality itself. The probability calculation. From theory to number, physicists are trained to turn mystery into mathematics. When the question became how long the universe can sit in its current vacuum, they didn't treat it poetically. They wrote an equation. It begins with the Higgs potential, the graph describing how the energy of the Higgs field changes with the field's own value. The curve looks like a shallow basin separated by a hump from a deeper basin far below. The shape of that hump, the barrier, decides the odds of transition. Higher barriers mean greater safety. But in quantum mechanics, even an infinite appearing wall leaks probability. To calculate how much leaks, theorists reach for one of the strangest ideas in all of physics: tunneling. Tunneling is the mathematics of the impossible. A particle trapped in a potential well can appear on the other side of an energy barrier without ever passing through it conventionally. Instead, its wave function extends under the barrier, decaying exponentially yet never reaching zero. The same principle applies to fields. The Higgs field as a quantum object has a wave functional amplitude for every possible configuration of the entire universe. Vacuum decay becomes, mathematically, a rare fluctuation of this field's global configuration, an instant when the field's amplitude seeps across the barrier into the true minimum. To compute the probability, theorists translate the problem into Euclidean, space imaginary time coordinates, where equations of motion resemble those of a classical system climbing a hill. Sidney Coleman and Frank DeLucia developed the framework for this in the late 197s. They found that the tunneling rate per unit, for volume, space multiplied by time, equals an exponential of negative action, g a xp source se os h. Here, se, the Euclidean action, is roughly the energy cost of forming a critical bubble of the new vacuum. H is Planck's constant, the measure of quantum agitation. The prefactor A represents fluctuations around that ideal solution. Every symbol hides staggering complexity, yet collectively they output one number, the decay probability density. To transform that into a cosmic forecast, one integrates G across space-time. Multiply by the volume of the observable universe and the age of cosmic history so far, and you obtain the cumulative probability that at least one critical bubble has appeared. At first glance, that number looks microscopic. Using experimentally measured Higgs and top quark masses, SE works out near 400 in natural logarithmic units. E400 is infinitesimal. But then recall the volume factor, roughly 1080 cubic meters multiplied by 4x 1017 seconds of history gives around 1097 cubic second meters. Even tiny rates can produce non-zero chances when multiplied by something that big. Physicists vary the input constants within their measurement uncertainties to see how sensitive the result is. The Higgs self-coupling, L, and the top quark Yukawa coupling, YT, both run with energy scale according to renormalization group equations. Past about 1010 GeV, L turns slightly negative, flattening the potential barrier. Changing YT by only a few parts in 1,000 can shift the sign of L and hence determine whether the vacuum is absolutely stable or metastable. When statistical sampling of those parameters is performed like rolling dice, billions of times through Monte Carlo methods, roughly 1 or 2% of the simulated parameter sets yield decay within the natural lifetime of the cosmos. That fraction becomes the headline, a 1 in 100 risk. It's vital to understand what lifetime of the cosmos means in this context. It's not the age of stars or the interval before galaxies drift beyond each other's light horizons. It's the future integral of cosmic expansion, the timescale over which space-time continues to exist in its present form. If we approximate that as tens of billions of years multiplied by factors from accelerating expansion, the theoretical horizon stretches to about 10 and 11 years. The 1 in 100 chance refers to decay within that entire horizon, not in the next millennium. On shorter timescales, the probability plummets to effectively zero. Still, 1% unsettles intuition. A 1% chance of failure in a device meant to last forever would be catastrophic engineering. Translating it into cosmic language challenges how we define safe. When theorists first saw that result, they didn't panic. They rechecked the algebra. Every constant became suspect. Could it be that the strong nuclear coupling, as measured to 0.1% precision, skewed the outcome? Perhaps gravitational effects at extreme energies, quantum corrections from the Planck scale, stiffen the barrier, making decay practically impossible. Such questions spawned hundreds of studies refining the number. Those refinements divide into two main approaches. The first works purely within the standard model, trusting its equations up to the Planck scale with no new physics intervening. The second introduces hypothetical additions, supersymmetric partners, heavy neutrinos, or unknown scalar fields that modify the Higgs potential at high energy. Each extra ingredient reshapes the curve. Most extensions raise stability, but the conservative estimate, the one scientists quote publicly, comes from the minimal model. Within that framework, metastability survives as the best fit to data. Let's translate the algebra into something tangible. Imagine the universe as an immense ocean. Somewhere beneath the surface lies a trench 30 kilometers deep, our false-to-true vacuum barrier. The chance that a random fluctuation of waves could tunnel an entire cubic kilometer of ocean water through that rock layer is vanishingly small. But extend this ocean infinitely in every direction, wait for billions of years, and the improbable becomes possible. One droplet may find the crack. In quantum terms, that droplet is the critical bubble radius, the smallest patch of true vacuum whose surface tension can't hold it back. Once formed, it expands at light speed, converting everything it touches. The bubble's critical radius, RC, follows from balance between wall tension, S, and energy difference, dV, between vacua. RC equals 3S, equals 1 dV. Insert standard model numbers, and you get sizes on the order of 10 to 27 meters, smaller than atomic nuclei. Yet within that microscopic zone sits the power to rewrite the cosmos. Calculating S and dV requires integrating the Higgs potential over the field's path between minima a mathematical journey across 60 orders of magnitude in energy. High-performance clusters run those integrals for weeks, adjusting constants within experimental uncertainties. The result reaffirms the same rough range, decay exponent between 350 and 450, translating to the 1% integrated probability. Where does dark energy enter? Because the universe expands, each extra cubic meter of space adds new opportunities for decay. The faster expansion proceeds, the more space exists to host tunneling events. But the vacuum energy driving that expansion dark energy also slightly raises the potential barrier. Two competitive effects intertwine. More volume increases risk, higher barrier decreases it. Current cosmological measurements set the dark energy density at 6.9 is 1027 kilon per cubic meter, a value that leaves us precariously balanced, neither perfectly stable nor doomed, a cosmic stalemate encoded in decimal precision. For perspective, consider how these probabilities compare with other cosmic risks. The annual odds of a civilization-ending asteroid impact are perhaps 1 in a million per year. Combine over 100 million years to reach 10% cumulative risk. Vacuum decay's 1% over trillions of years is incomparably smaller on human scale. Yet philosophically, the two numbers share meaning. They're statements about inevitability given sufficient time. The same logic that ensures radioactive atoms eventually decay assures that metastable universes don't last forever. The timescales differ, not the principle. To express the tunneling rate more directly, physicists define a dimensionless lifetime parameter, v tosens GH4, comparing decay rate to the Hubble volume's growth rate. If V1, the vacuum is effectively stable across cosmic expansion. Our best estimates give V 10 to 4, comfortably below unity but not zero. That small deviation encapsulates our uncertainty about existence. In essence, the cosmos renews its lease on being each moment with probability 999, repeating, but the series eventually fails. Every calculation hides approximations. The Coleman-de Lucia formalism assumes perfect homogeneity and neglects gravitation beyond first order. Including full general relativistic corrections slightly reduces risk. The curvature of spacetime adds energetic cost to bubble formation. Finite temperature effects from early cosmic epochs would have increased rates, but only when the universe was less than a second old. Since then, it's been too cold for thermal catalysis. Even using conservative corrections, the result remains metastable. The barrier is tall, not infinite. Beyond analytic formulas, numerical models visualize the energy landscape as color maps. Valleys of low potential, ridges of instability, plateaus extending to Planck-scale energies. Shaded red for danger zones, the plots show a narrow yellow contour cutting through a metastable corridor where our measured constants fall. That narrowness fascinates researchers. It's as if, among infinite possible combinations of particle masses, ours just happens to sit near the edge of survival. Increase the top quark mass by 1 kilo electron volt per billion, and the contour slips toward instability. Decrease it, total stability returns. The universe, it seems, likes living dangerously. From a methodological standpoint, the translation from field theory to numbers proceeds through 4 steps. First, determine the running couplings of all relevant parameters using renormalization group equations up to high energy. Second, extract the effective potential including 2 loop corrections. Third, solve the bounce equation, a differential equation describing the field's trajectory through imaginary time connecting false and true minima. Fourth, compute the action of that bounce and exponentiate it to get the tunneling rate. Each stage demands supercomputing power and precise laboratory data. It's the physics equivalent of weather modeling for eternity. As data improve, the uncertainty ranges tighten. Before the Large Hadron Collider's discovery of the Higgs, estimates of vacuum stability spanned 10 orders of magnitude. After 2012, the spread narrowed dramatically. By 2024, with improved top quark mass averaging and gluon fusion cross-sections, the metastable interpretation dominated. Statistical meta-analyses combine dozens of studies and yield median global fit. Decay time, t, 1036 years, confidence interval stretching from 1030 to 1048 years. Yet because those bounds enter an exponential, even minor shifts, rescale probabilities drastically. Expressed over the entire cosmic future instead of fixed years, the integrated risk condenses to about 1%. It's worth pausing to appreciate the precision implied. We're assigning numerical odds to the endurance of everything space, time, matter, light based on experiments performed in subterranean tunnels beneath Geneva. A handful of measured resonances and particle masses feed equations that pronounce the universe probably safe. The hubris might seem comedic, but the mathematics has tested itself in countless other domains, from atomic spectra to galaxy formation. When theory and observation match over 14 orders of magnitude, extending the same logic. One order further is less arrogance than continuity. Some researchers attempt intuitive metaphors for the magnitude of the risk. Imagine drawing one marble from a jar containing 100 identical copies of our universe. 99 marbles survive unchanged. One vanishes the instant you touch it. That's the scale of uncertainty embedded in physical law. But since we can never rerun the experiment, the metaphor stays philosophical. All we can do is measure more precisely, hoping the numbers shift downward toward absolute stability. Every incremental improvement in top quark mass measurement, every decimal cut from error bars, acts as another assurance policy for existence. Intriguingly, the 1 in 100 estimate lines up with another domain of physics, the anthropic landscape predicted by string theory. In that framework, the universe can occupy an enormous number of metastable vacua 10^500 or more, each with different constants. Statistically, only a fraction lasts long enough for galaxies to form. Our 1% hazard fits that distribution neatly. A universe stable enough for life but not immortal. It's another piece of circumstantial evidence suggesting we belong to a broader ensemble of realities still fluctuating among configurations. What then would a more precise risk assessment require? Better measurement of three quantities: the Higgs mass, MH1 125.09, plus 12 GeV, the top quark mass, 272.6 ∗ 3 GeV, and the strong coupling constant as Gwan 11 Improve any by an order of magnitude and the stability boundary sharpens. Planned colliders, the Future Circular Collider in Europe and the International Linear Collider in Japan, aim to achieve exactly that. Within a few decades, we may know whether the universe's safety margin is 1% or 0.01%, or conversely whether new physics guarantees eternity. Until then, metastability remains the statistically favoured state. From a philosophical perspective, numerical precision doesn't change the emotional result. Knowing the universe might flip with 1% probability over eternity alters nothing we do, yet the calculation itself carries beauty. It ties together quantum uncertainty, cosmic expansion, and particle physics in one coherent equation. That unity of scale from the subatomic to the universal is the same thread Einstein sought in his field equations. Vacuum decay stands as one of the few phenomena where all regimes meet, quantum mechanics, relativity, and statistical cosmology intertwined. So after decades of computation and debate, the conclusion stands. Our cosmic home is not guaranteed but overwhelmingly likely to continue. The 1 in 100 number is less prophecy than punctuation, a reminder inscribed in logarithms that existence itself sits within probability's domain. For practical life, it's meaningless. For philosophy, it's everything. It means stability is empirical, not absolute. It must be measured, maintained, and never assumed. As equations reach further precision, they whisper the same refrain. The universe endures not because it must, but because, so far, the math allows it. The trigger mechanism. How decay begins. If the universe ever ends through vacuum decay, it won't begin with spectacle. There will be no cosmic explosion, no visible sign, not even a flicker of warning light. Everything, everywhere, will continue behaving normally until a single quantum fluctuation crosses a hidden threshold. Then, in one location smaller than an atom, the Higgs field will slip through the barrier that has held it for billions of years, and a new phase of reality will appear. The event will be utterly local, an infinitesimal crack in the scaffolding of physical law, but in that crack, the entire universe will eventually fit. To see how such a transformation begins, think about the landscape we described earlier, the energy valley of the Higgs field, separated from a deeper one by a ridge. The field sits near the bottom of the first valley in what seems a steady equilibrium. But quantum mechanics refuses absolute stillness. Every field vibrates with uncertainty, jittering by amounts defined by Planck's constant. Most fluctuations fade. A rare few momentarily shift the field further up the hillside. Very rarely indeed, a fluctuation might be large enough that a tiny region of the universe momentarily tunnels through the ridge, landing on the far side in the deeper valley. That microscopic pocket becomes the seed of the new vacuum. In classical physics, nothing with less energy can cross an upward barrier, but in quantum mechanics, every forbidden path has a finite amplitude. A better analogy is a candle flame flickering across wax. Most waves of heat fizzle, but one might randomly create a pit where the structure of combustion changes. At that instant, the local balance of energy reverses. The true vacuum is of lower energy than the surrounding false one, so nature favours expansion of that state. As soon as a region large enough to overcome surface tension forms, Roughly when the gain in volume energy exceeds the cost of its boundary, it begins to grow. The radius at which that occurs is called the critical radius. Mathematically, the critical radius follows the same balance that governs droplets forming in rain clouds. Surface tension resists growth. Internal pressure drives it. In vacuum decay, the pressure is the energy difference between vacua, dV. The surface tension is the energy stored in the field gradient across the bubble wall. When 3s bashkashus rdv, the forces equalize. Anything smaller collapses back into false vacuum. Anything larger expands unstoppably. The equations describing this transition are direct descendants of work done in the late 197s by Sidney Coleman, later extended with Frank DeLucia to include gravitation. In their model, you can picture the universe flipping quantumly from one state to another along a path of least action, a trajectory drawn not in space but in configuration space, the exhaustive map of every possible field value. The moment a sufficiently vigorous fluctuation pushes the Higgs field beyond that crest in one infinitesimal volume, an entire region adopts the new lower energy configuration. It is as if the universe, everywhere constant in its properties for eons, suddenly encounters an alternative rulebook and switches allegiance. The conversion releases energy equivalent to the vacuum energy difference multiplied by volume. In ordinary physical units, even a cubic meter undergoing that shift would liberate more energy than all stars combined in the same region. Yet that energy doesn't emerge as heat or light in any recognizable form. It manifests as motion of the bubble wall itself, space-time reshaping to the new vacuum's geometry, converting potential energy directly into expansion. What makes this mechanism so unnerving is its self-sufficiency. No external trigger is needed once conditions exist. Quantum tunneling requires only possibility. The field explores all configurations continuously, and the universe's sheer volume provides infinite trials. Somewhere, sometime, a patch succeeds. The event requires no catalyst, no cosmic ray impact, no stellar collapse. Those scenarios can modify rates slightly, but the driving cause remains intrinsic instability. Even if the probability per cubic light year per billion years is unimaginably tiny, the value isn't zero. Given eternal time, the forbidden happens. Still, physicists examine circumstances that might nudge probability. One is curvature regions near massive concentrations of matter, like black holes. Extreme gravity warps spacetime so sharply that quantum fields behave differently there. In the early 201s, theorists discovered that small black holes could in principle catalyze vacuum decay by concentrating quantum fluctuations near their horizons. The intense curvature reduces the effective energy barrier locally, making tunneling more likely. But subsequent analysis balanced the picture. Black holes evaporate through Hawking radiation, and that emission tends to stabilize nearby fields. The competing effects nearly cancel. Even within galactic cores, the rate increase is negligible. Temperature provides another subtle variable. At the dawn of time, when temperatures exceeded 1 trillion Kelvin, thermal energy rivaled particle rest masses. The Higgs field danced across its potential, and minor perturbations could have driven it into different minima. Somehow, during cosmic inflation and subsequent cooling, the field landed safely in the metastable pocket we now occupy. Today, at 2.7 Kelvin, the universe is too cold for thermal activation to matter. The only remaining risk is pure quantum tunneling energy uncaused, arising from uncertainty itself. This distinction matters because it clarifies that no human experiment can plausibly trigger such a catastrophe. When the Large Hadron Collider first began smashing protons together at tera-electron-volt energies, public anxiety briefly erupted. Could those collisions spark a bubble of true vacuum? The numbers make the fear laughable. The required energy corresponds to 1010 GeV within a region of roughly 10 to 26 meters. Earth's most powerful machines reach 104 joule GeV spread over meters sextillions of times short. Meanwhile, cosmic rays striking our atmosphere routinely exceed LHC energies by factors of 1 million and have done so for 4 billion years without consequence. If high-energy collisions could puncture reality, we'd never have evolved to worry about it. Another possible contributor is quantum gravity unknown physics at the Planck scale. Coleman and DeLucia already included basic gravitational effects, showing that space-time curvature slightly modifies tunneling action. Some later studies argue that integrating full quantum gravity could either suppress or enhance decay dramatically. No consensus exists because nobody yet knows the correct unification between quantum field theory and gravity. Some candidate models, like string theory, introduce additional scalar fields that automatically stabilize the vacuum. Others predict vast landscapes of potentials dotted with metastable wells. Within that landscape, our own local depression might actually be one of the more durable ones. The subtlety here is timing. Tunneling doesn't occur evenly. Its likelihood accumulates statistically. Each additional moment multiplies the survival probability by 1 GV dt, where GV is the decay rate per spacetime volume. Think of a radioactive isotope with trillion-year half-life multiplied by the cosmos's huge volume, and small probabilities integrate into finite risk. But even if a bubble formed today, its origin would be microscopic, buried somewhere in intergalactic voids or perhaps within a star. Because its wall expands at light speed, no external observer, even theoretically, could detect it before it arrived. There's no causal mechanism for forewarning. Visualizing the process breaks intuition. The bubble doesn't explode outward like a bomb in space. Rather, the boundary between true and false vacuum is the only region of change. Inside, space itself follows new rules. The speed of light, fundamental masses, electromagnetic constant, all redefine according to the deeper minimum of the Higgs potential. Outside, for a fleeting instant, everything remains as before. The frontier moves outward at exactly the limiting velocity of information, rewriting space-time as it passes. To external observers, it's invisible. To those engulfed if observation were possible, it's instantaneous. Interestingly, theoretical physicists have toyed with computer simulations of this transition. On digital lattices representing field configurations, they program conditions mimicking metastability, then introduce random fluctuations. Almost always the simulated field remains stable until one fluctuation spontaneously generates a spherical region slightly in the lower energy state. The region collapses unless its radius exceeds the critical threshold. When it does, the simulation fills the frame with a wave of color analogous to the bubble swallowing the grid. The exercise doesn't prove anything cosmically, but it demonstrates how statistical inevitability emerges from random noise. So when cosmologists speak about the trigger, they aren't referring to a deterministic switch. They mean that mathematics allows, at some unpredictable moment, the universe to prefer a slightly different configuration and to adopt it socially, so to speak, through contagion at light speed. In philosophical language, existence contains within itself the seed of its own redefinition, encoded in probability. Even if one could point to where such an event began, individuality breaks down. All coordinates and measures depend on the vacuum's constants. The moment those shift, reference frames dissolve. The bubble's center from our perspective might correspond to a single moment in our space-time, but inside its own physics, that same moment occupies infinite breadth. The new vacuum carries its own units, its own time parameter. From within, there is no sense of eruption. There is only continuity under new physical law. Could nature's own processes ever make tunneling more likely on observable scales? Perhaps during violent events like neutron star mergers, where densities reach nuclear levels. Yet even those extremes remain 20 orders of magnitude below the Higgs potential barrier. Magnetic fields, shock waves, relativistic jets, all trivial compared to the required energy density of 1037 joules per cubic meter. The barrier is safe by absurd margins. The theoretical risk arises not from exceptional energy, but from extraordinary patience. Eternity is long enough for anything permitted to occur once. In the language of quantum field theory, the amplitude for remaining in the false vacuum decays exponentially with 4 volume according to PT, Bach xpt Vt, where Vt represents the cumulative spacetime volume accessible up to that moment. Since the universe's expansion accelerates, Vt increases faster than T4. That means the exponential suppression eventually loses out. Given unlimited time, P approaches 0. So long-term instability is not conjecture. It's a mathematical corollary of time's infinity. Paradoxically, this inevitability contains reassurance. Because the probability per moment is minuscule, human concerns remain untouched. The half-life may dwarf any conceivable future. But it also teaches a kind of cosmological humility. There are processes that don't require cause and whose consequences we'll never experience. Vacuum decay exists as a possibility woven into the same equations that give us sunlight, matter, and thought. Some theorists wonder whether the trigger could appear as a cascade rather than a single event multiple microbubbles forming whose collisions accelerate the transition. In early universe phase changes, such bubble collisions generated gravitational waves. Were that ever to happen again, the pattern might leave faint signatures permeating the new universe's background, echoes of the old physics dissolving. But to us, any prelude is undetectable. We inhabit the false vacuum's blind spot, unable even in principle to map its impending transformation. Ultimately, the trigger mechanism reduces to an unavoidable statement about quantum reality. What can happen will happen given enough space-time. A single fluctuation, smaller than a proton, is enough. No cosmic deity of destruction, no lab accident, just mathematics unfolding with infinite patience. If that's unsettling, it's also strangely elegant. The universe requires no external hand to end. It carries termination as naturally as birth. The same principles that allowed a primordial field to inflate into galaxies grant that field permission one day to settle more deeply into itself. Understanding this offers an unexpected comfort. The laws that might someday erase everything are the same laws that sustain everything now. Beneath terror lies symmetry, creation and annihilation as mirror phases of one process. The vacuum that could betray us is also the vacuum that lets atoms exist. Photons travel, hearts beat. The trigger is not a ticking bomb hidden in physics. It's a reminder that permanence was never promised, and that the rules of reality remain consistent even at the end of reality itself. Cosmic implications, rewriting physical laws. If the Higgs field ever tunneled into its deeper valley, the change wouldn't simply rearrange particles, it would redefine the dictionary of physics itself. The true vacuum would occupy a different minimum of the Higgs potential, and that means every constant derived from it would shift. The electron's mass, the strength of electromagnetic attraction, the speed of light, even the shape of space-time, all would recalibrate to new values. To the existing universe, that adjustment would be indistinguishable from erasure. The old laws would no longer apply. Their equations would go discontinuous, their solutions meaningless. Consider how everything we know relies on a delicate network of numbers. The electron mass is roughly 1/1000th that of the proton. Because of that ratio, hydrogen forms stable atoms, stars burn at sustainable rates, and chemistry produces complexity. Gravity's weakness compared with electromagnetism allows planets to orbit rather than implode. Planck's constant, the fine structure constant, the cosmological constant, each defines the pattern of possibility. A new vacuum wouldn't tweak them slightly. It could remake them wholesale. Change them by as little as 1%, and molecular bonding fails. Change them by 10%, and even protons can't exist. In that sense, vacuum decay is the opposite of ordinary catastrophe. Nothing happens in the drama movie sense. Rather, everything that could possibly happen under the old rules becomes undefined. You could say the act of existence renormalizes. The fields that once set forces and masses oscillate into new equilibrium values. The symmetries of the standard model might break differently or not at all. Some gauge interactions might vanish, others combine. If the Higgs field expects a higher resting value, particles would become heavier, compressing the typical scale of matter to microscopic densities. If lower, matter itself would lose cohesion and diffuse into radiation. The gravitational constant, g, ties space-time curvature to energy density. Alter the vacuum energy, and you alter spacetime's relaxed shape. In a lower energy state, curvature could become more positive, leading to a big crunch inside the new bubble, collapse following creation. In a higher energy state, vacuum pressure turns repulsive, igniting fresh inflation, a runaway expansion, birthing a separate universe. Both outcomes are symmetrical around the same idea. Shift the baseline of vacuum energy, and the geometry of reality remakes itself. Early descriptive attempts compared the process to phase transitions familiar from condensed matter physics. When water freezes, its hydrogen bonds align, lowering internal energy. Molecules don't burn, they find a more orderly arrangement that releases latent heat. Vacuum decay follows the same blueprint, but the latent heat is the vacuum energy difference, immense beyond measurement. That energy becomes curvature. It doesn't propagate as heat we could notice, it becomes the fabric of space racing outward. The surface of the bubble is analogous to the interface between phases, sweeping out a new metric, the set of relationships defining distance and time. Inside it, physics adapts instantly. Outside, it hasn't yet been recompiled. From within, observers, if such could exist, would experience neither flash nor blast. To them, their constants would appear perfectly normal. Clocks would still tick in local seconds, rulers would still measure local meters, no history of the prior universe would survive. The technical term is causal disconnection. The bubble's interior evolves under new parameters that cannot communicate backward through the boundary. Whatever came before becomes unreachable, not destroyed in the conventional sense, but rendered nonsensical under the new metric. This prospect raises profound questions about what annihilation even means. If the new universe contains consistent physics, matter, and perhaps eventual complexity, then the old universe hasn't ended. It has transformed. Our own Big Bang might have begun as such a transition within a prior false vacuum. Inflation theory already demands an enormous release of vacuum energy to power the universe's initial expansion. It's possible that the destruction of one cosmic domain was the creation of another. From that angle, vacuum decay isn't death, it's reproduction. On smaller conceptual scale, the rewriting of laws exposes how intertwined fundamental constants are. The Higgs field couples not only to leptons and quarks, but also to the W and Z bosons that mediate the weak force. A change in the Higgs-Vevey, the vacuum expectation value, reshuffles those boson masses, thereby shifting decay rates of particles, altering nuclear reaction chains inside stars. In the new vacuum, fusion as we know it might never occur. The periodic table could vanish before even the first element stabilizes. Imagine, for argument's sake, that the new constants permit atomic structure, but with drastically different balances. If electrons were twice as massive, orbitals would shrink to half their radius. Chemical reaction rates would soar. Quantum tunneling in biochemistry would dominate, leaving any form of stable metabolism impossible. If electromagnetism weakened while gravity strengthened, stars might ignite at temperatures too high for planetary systems to survive. Every conceivable arrangement of new parameters leads to monotone results. Universes either so uniform that nothing happens, or so violent that nothing lasts. A particularly unsettling implication involves light itself. The parameter c, the speed of light, depends on the electrical permittivity and magnetic permeability of the vacuum properties that arise from the fields populating space. A new configuration means a new c. Time and distance, being defined relative to light's travel, reshape accordingly. To an interior observer, no discontinuity appears. Their units scale automatically, but from the perspective of our current physics, it's equivalent to remapping the coordinate grid. Distances, durations, and even energy equivalences change meaning. In certain models, the fine structure constant A, roughly 137 today, drifts with the Higgs Vive. If A were even 1/100, quantum electrodynamics predicts electrons would collapse into nuclei. If smaller, atoms wouldn't bind. Thus, the reaction defining light emission in which electrons jump between energy levels would cease. The new vacuum might have no starlight, merely a dull uniform field of energy still satisfying its own equations. Darkness wouldn't be a matter of extinguished stars, but of fundamental optical impossibility. Another domino concerns quantum chromodynamics, the field theory describing how quarks bind via gluons. Its coupling constant, often denoted as, runs with energy scale and depends indirectly on the Higgs field through renormalization. Change the Higgs baseline and quark confinement could vanish. Nuclei might disintegrate into free quarks, or, inversely, bind so tightly that the entire bubble becomes instantly neutron star dense. In that scenario, The universe reborn from our ashes would be compact, dark, and effectively frozen, an eternity of degenerate matter. These possibilities sound speculative, but they follow directly from the equations linking coupling strengths to vacuum expectation values. We can explore them mathematically because the Standard Model is explicit about dependencies. For instance, the Yukawa coupling Y determining particle mass scales as MyV, where V is the Higgs VV. Double V, you double all masses. The Bohr radius of hydrogen, proportional to 1 ⁻⁴ μA, shrinks accordingly. Atomic volumes fall by powers of 8. The stability of matter becomes arithmetic tragedy. Then comes gravity's complicity. The cosmological constant, L, essentially the energy density of the vacuum sets, the curvature of space when all matter withdraws. Lower the vacuum energy, and L could turn negative, making overall geometry closed. The new bubble might recollapse within seconds of its own time. Raise it, and expansion accelerates uncontrollably, perhaps producing inflation anew. In both directions, structure fails. Hence, an alternate vacuum doesn't mean a gentler or harsher place. It likely means no place at all, a realm where definitions of distance or duration evaporate. Quantum field theorists describe this phase change through symmetry breaking and restoration. Our universe exhibits broken electroweak symmetry. The Higgs field's non-zero value differentiates the electromagnetic and weak forces. In a deeper vacuum, that symmetry could be restored, no difference between photon and W boson. Electromagnetism as a separate interaction might disappear. Without it, chemical bonding vanishes. Charged particles have no meaning. Everything dissolves into a uniform soup of neutral interactions following new gauge rules. From the standpoint of cosmology, the new region would rapidly reach thermal equilibrium according to its own constants. Temperatures, durations, and energy densities would renormalize almost instantly. Within microseconds relative to our clocks, the new universe's properties would settle. If curvature produced runaway expansion, inflation would stretch the initial region from subatomic size to cosmic dimensions. Quantum fluctuations under those conditions could seed matter distributions, starting the long chain leading to galaxies, and, eventually, perhaps life under laws unrecognizable from ours. The elegance here is circular. The same equations predicting our end also describe our beginning. When inflation ended 13.8 billion years ago, the universe cooled into a particular vacuum, the false one we now occupy. The slight residual energy we call the cosmological constant accelerated expansion later. If our vacuum decayed again, that residual would reset, possibly creating the inflation field for whatever comes after. Thus, vacuum transitions act as gears in cosmic evolution. The universe isn't an artifact. It's a process repeatedly reconfiguring its own code. In string landscape theories, each possible vacuum corresponds to a different way of compactifying extra dimensions. The transition from one to another rewinds that geometry, refolding the hidden dimensions differently. The result is a universe with altered particle content and force balances. So not only constants but the very taxonomy of matter would change. There might be no analogue of quarks, no fields resembling those we know. Mathematicians describe this as topology change. Space-time's shape shifts, and therefore its permitted laws change. Our doom could be another universe's initialization action, its own symmetry-breaking event that writes entirely new physics upon the canvas. Suppose, improbably, that awareness persisted during the early moment of transformation. What would we experience? Nothing recognizable as collapse or pain. The transition propagates faster than neural signaling, replacing the substrate of matter before a thought completes. Consciousness, being an emergent pattern in physical interactions, would dissolve with its host constants. The sensation wouldn't be destruction, but abrupt absence, the cessation of definable process. No time to register, no medium to remember. In the quantum bookkeeping of the cosmos, awareness would sum to zero without residue. To glimpse the magnitude of the change, calculate energy density differences predicted by metastable models. The false-to-true vacuum gap might be around 108 joules per cubic centimetre. Multiply by the volume of Earth, and you obtain 241 joules, 10 billion times the Sun's total lifetime output. That energy doesn't explode outward. it reforms spacetime geometry itself. Physicists often emphasize that statement. Energy release doesn't produce heat inside old physics because heat presumes the old metric. Instead, the bubble front converts potential energy straight into motion in new coordinates. The release is total and perfectly smooth, the quietest violence imaginable. This conceptual silence challenges the metaphor of destruction. Vacuum decay would end our laws but not lawfulness itself. The transition would be continuous with the mathematical structure of physics. The Lagrangian would rewrite into a new form still internally self-consistent. If nature favors symmetry and minimal action, then the new vacuum simply obeys an updated minimum of the same principle. Continuity hides within discontinuity. Fundamental logic remains intact even as its parameters change. Viewed altruistically, the event could be seen as cosmic creativity. Each vacuum transition opens possibility space billions of times broader than before. Perhaps universes of varying constants continually arise, most collapsing quickly, a few achieving longevity like ours. From that eternal experiment comes diversity of physics, and perhaps somewhere consciousness reborn under new metrics, contemplatively tracing equations to the same stunned recognition. Stability is temporary, but elegance is eternal. Philosophically, the notion of rewriting laws also rewrites the idea of permanence. We often imagine the laws of nature as absolute outside time. Vacuum decay undermines that assumption. It implies that physical law evolves, that constants are contingent expressions of deeper processes still running. The laws of physics aren't commandments. They're stable configurations that happen to work for a while. In that light, the looming possibility of decay becomes evidence for dynamism at the heart of reality. Even foundations can change, not arbitrarily, but according to consistent mathematics, exploring its own landscape for lower energy, higher symmetry, greater simplicity. This insight blurs categories of beginning and end. If vacua can transition endlessly, then the universe has neither origin nor finale only, states of relative stability punctuated by updates. Existence becomes an algorithm minimizing potential energy through unending cycles. Our comfort with fixed rules gives way to admiration for the flexibility of nature's code. From that viewpoint, the potential rewriting of physical laws is less a threat than a proof that the system works. It adapts, self-optimizes, generates novelty. Still, for those bound to the current rules, there is poignancy. Every poem, every memory, every flavor depends on constants that could, without malice or purpose, dissolve. Yet that impermanence connects us more intimately to physics. The photon that left a star yesterday follows the same Maxwell equations that make neurons fire and hearts beat. If those equations someday change, their transformation will carry traces of that same coherence. To exist at all is to participate in a process capable of such transformations. Ultimately, the cosmic implication of vacuum decay is radical but serene. Reality is not a fixed document, but an editable language. Should the edit occur, it will happen according to grammar so flawless that even disappearance reads like continuation. The universe would not scream. It would rewrite itself with mathematical grace, deleting nothing, preserving symmetry through change. Perhaps that's the greatest reassurance physics can offer, that even in collapse, consistency endures, and beneath annihilation lies the quiet certainty that the laws, whatever they become next, will still make sense. Human beings are explorers by nature, allergic to mystery left unresolved. Faced with any theoretical danger, our first instinct is to ask, could we detect it before it happens? But when the hazard is vacuum decay, that question acquires an exotic twist. We aren't talking about a supervolcano or asteroid, but a quantum restructuring of reality itself, a process moving at light speed that erases every instrument the instant it arrives. The honest answer begins and ends with humility. In principle, no detection is possible. Yet that doesn't stop physicists from asking, what if? And devising ingenious ways to probe around the edges of impossibility. To understand how they think, imagine peeling the catastrophe back one layer. The object of study isn't the expanding bubble. We'll never see that. It's the instability leading up to it. What can we measure about the false vacuum today that might hint at its fragility tomorrow? In physics terms, detection becomes prediction not of the event, but of the precursors written into the equations that allow it. The most direct route begins in particle accelerators, because those machines literally shake the Higgs field. Every high-energy collision disturbs the local vacuum just enough to sample its properties. When two protons collide at multi-tera electron-volt energies, the quantum foam between them vibrates with transient field excitations. The frequencies and cross-sections of those excitations constrain the Higgs potential. If the vacuum were less stable, tiny anomalies would appear, deviations in decay rates, production channels, or self-coupling strengths. By comparing billions of particle events, researchers can, in theory, map subtle wrinkles in the energy landscape that holds our existence. In practice, this search is statistical archaeology. At the Large Hadron Collider, detectors record collisions producing Higgs bosons, photons, and jets. Then analysts reconstruct distributions with mathematical fits. A small shift, say, a measured trilinear Higgs coupling, slightly lower than the standard model predicts, might hint that the potential barrier is thinner than expected. Another clue lies in off-shell Higgs production, where the particle's virtual presence influences reaction probabilities far from its mass energy of 125 eV. Each discrepancy, however minute, contributes to a global picture. Is our vacuum perched on a plateau or teetering on a cliff? Future colliders aim to refine that picture drastically. The proposed Future Circular Collider at CERN would smash particles at 100 TeV, almost an order of magnitude above current energies, and measure Higgs self-interactions to within 3%. The International Linear Collider, envisioned as a cleaner electron-positron machine, would isolate quantum corrections from messy hadronic backgrounds. Together, these projects seek signatures of stability. Does the self-coupling L remain positive up to the Planck scale, or does it bend downward into negative territory? A continuous positive trend implies safety. A dip confirms metastability. In that sense, each data point becomes a cosmic EKG reading, the faint heartbeat of space-time's health. Yet accelerator data describe only the potential shape, not any ongoing process of decay. What about indirect cosmic observation? Could we, in principle, notice a bubble forming far across space? The naive idea is to look for expanding spheres in the cosmic microwave background, the ancient afterglow of the Big Bang. If a patch of the universe had already transitioned into a different vacuum and its boundary happened to intersect the region that emitted our CMB photons, the map might show a circular anomaly, a subtle cold or hot spot representing the imprint of changed physics. Cosmologists have hunted for exactly such signatures. The Wilkinson Microwave Anisotropy Probe and later the Planck satellite examined the CMB sky with microkelvin precision. Within those patterns, they looked for features too symmetrical to be natural perfectly round disks where temperature correlations step abruptly. None matched. The observed anisotropies are Gaussian noise, seeded by primordial inflation, not by vacuum transitions. Still, the search continues. Each new all-sky survey effectively asks, has any region beyond our cosmic horizon already made the leap, and might we someday see its edge approaching? The silence of evidence so far doubles as reassurance. If decay happened nearby in the last 13 billion years, its front would already have reached us, and it hasn't. Gravitational wave astronomy provides another window. In theory, bubble collisions during vacuum transitions release ripples in spacetime across a spectrum from milli to nanohertz frequencies. Instruments like LISA, the Laser Interferometer Space Antenna, scheduled for the 203s, may detect stochastic backgrounds from ancient phase changes. Such detection wouldn't mean ours is collapsing, but it would confirm that the universe has experienced similar events. Knowing that metastable domains really do transform elsewhere would change our understanding from speculation to precedent. It would prove that false vacua, however long-lived, eventually surrender, and that detection requires listening, not looking. Nevertheless, all these approaches share a sobering boundary. They can reveal susceptibility, never immediacy. Quantum tunneling isn't preceded by microcracks or slow drifts. It's fundamentally random. The system doesn't prepare to decay, it simply does or doesn't. Unlike a volcano accumulating strain, the Higgs field has no gauge of approaching catastrophe. Its potential energy remains constant until, by random fluctuation, a point of the field configuration fits the critical profile. Even if we could map every grain of energy density in the observable universe, that knowledge would yield no countdown clock. Still, theorists enjoy probing the impossible. Some suggest that detection could arise from secondary quantum correlations. Because tunneling is a non-local phenomenon, the entire field configuration shifts along a least action path. Perhaps quantum entanglement could carry faint precursive signatures within the field's zero-point fluctuations. In other words, before decay, the uncertainty distribution might momentarily distort in measurable ways, altering the statistical noise we detect in laboratory quantum systems. Experiments comparing ultra-stable atomic clocks or superconducting qubits across large distances could, hypothetically, register such correlations. None currently show anomalies, but the idea is conceptually fascinating, reality rumbling softly before rewriting itself. Another speculative route involves astrophysical messengers. The Higgs field permeates all space, including regions of intense curvature around black holes or neutron stars. If those objects subtly modify vacuum parameters, we might observe deviations in pulsar timing or gamma-ray spectra compared to theoretical predictions. Consistent discrepancies could indicate that the field's effective potential varies across the cosmos, an indirect sign of approaching instability. Yet no such regional variations have been detected. Across billions of light-years, the constants of nature remain stubbornly uniform to better than 1 part in a million. The vacuum, if false, is steadfastly consistent. What about simulation? Modern cosmologists often run immense numerical models evolving the Higgs potential across hypothetical universes. In these, they insert random quantum perturbations and compute decay events within simulated space-time cubes. The goal isn't to predict our timeline, but to generate probability distributions of bubble formation frequencies and expansion geometries. By comparing such virtual universes with the observed smoothness of our own, they place limits on how unstable it can be. If our vacuum were near critical instability, we'd likely see residual scars, anisotropies caused by nearby decays during inflation. The absence of such scars constrains decay rates to less than 1 per Hubble volume per 10 billion years, which matches the current theoretical 1% horizon risk. Even so, the allure of direct detection persists. Suppose, for argument's sake, a bubble did form somewhere 10 billion light-years away. Could any light or neutrino emission accompany it, perhaps enough to betray its birth? Unfortunately, no. The bubble wall travels exactly at light speed, meaning no ahead-of-front signal can outrun it. Any radiation generated within the wall's zone is confined behind it, redshifted, and then annihilated by the new physics it carries. There's nothing for telescopes to intercept. In relativity's language, the boundary is null. Causal lines tangent to it both originate and end at the same instant. To external spacetime, it's effectively invisible. Some researchers stretch creativity toward the multiverse for optimism. If other bubble universes exist beyond ours, and decay transitions can occur repeatedly, their gravitational signatures might seep between domains. Long wavelength tensor modes, essentially deep space ripples, could cross boundaries without needing continuity of matter. Detecting unexpected patterns in the cosmic gravitational wave background might hint that nearby vacua have already decayed. Even this idea has limits. Any crossing signal would be diluted by expansion by the time it reached us. But conceptually, it ties detection to eternity listening for echoes rather than alarms. Laboratory efforts focus instead on confirming the vacuum's uniformity as precisely as possible. Atomic clock networks comparing transition frequencies of different elements look for slow drifts that could indicate change in the fine structure, constant A. If A slightly evolved, spectral lines from distant quasars measured today would differ from their laboratory counterparts. After decades of observation, such drifts remain below 1 part in 1017 per year. Similarly, resonant mass detectors search for transient, stochastic variations in local vacuum energy minute pressure changes in the quantum fields surrounding mirrors or optical cavities. None have reported deviations beyond experimental noise. The negative result, ironically, becomes good news: stability verified once more. Meanwhile, theorists refine models of vacuum decay incorporating gravitational back reaction. In these, they ask whether micro-black holes created by high-energy cosmic rays could leave trace signatures if they briefly catalyze tunneling before evaporating. The expected event rate is minuscule, perhaps one in the observable universe every 10-30 years, but the mathematics yields potential byproducts, bursts of high-frequency gravitational waves or exotic particle emissions. Searches in archival data from LIGO and gamma-ray observatories return nothing, reaffirming that such events, if possible, are beyond our epoch's reach. At this point, the pursuit of detection veers into philosophy. Knowing beforehand may be impossible, but striving to know anyway defines science. The attempt itself yields discoveries peripheral but profound. In calibrating detectors to seek microsignatures of instability, researchers achieve unprecedented accuracy in constants, timekeeping, and field uniformity. The vacuum's apparent silence fuels ever better instruments, revealing subtler phenomena. Quantum noise limits, gravitational wave backgrounds, interstellar magnetic structures that have nothing to do with cosmic doom, but everything to do with understanding. The quest for the impossible becomes a driver of precision. Imagine for a moment what a partial success would mean. Suppose one ultrastable frequency comparison suddenly diverged, all devices worldwide noting the same fractional shift at the same instant. Physicists would scramble to analyze possibilities: local gravitational wave, shift in A, anomaly in atomic masses. If all conventional causes failed, the event would amount to nature clearing its throat, a preface with no body. Would that be warning of vacuum decay? We'd have no way to know. The observation would dissolve once new physics arrived less than a femtosecond later. In a sense, every measurement we take is the universe confirming, still here, up to the moment it ceases to answer. Understanding the deep reason behind undetectability requires returning to relativity's geometry. Imagine a Minkowski diagram of space-time with light cones spreading from every event. Vacuum decay's bubble wall traces a light-like path, the rim of those cones. Its interior replaces causal order. For any external observer, signals travelling at or below light speed can never reach beyond that frontier before being overtaken. Hence, all communication about the process is temporally localized to the instant before absorption. The entire cosmos could host countless independent decay fronts expanding simultaneously, yet each region would only notice its own arrival. Detection anywhere is equivalent to participation. That conclusion has a strange beauty. It preserves fairness across existence. No region enjoys advance notice. No place is privileged to see the apocalypse in slow motion. Every point in space-time shares identical probabilities and identical blindness. The universe remains democratic even in its annihilation. Still, in theoretical parlance, physicists discuss precursors, statistical phenomena that may correlate weakly with long-term decay probability. Among these are shifts in cosmic parameters like dark energy density. If future measurements from next-generation observatories, such as the Euclid mission or the Nancy Grace Roman Space Telescope, ever detect the cosmological constant increasing modestly over time, that might imply the underlying vacuum potential is sliding along its slope. But the effect would be so small as to require trillions of years to double. We wouldn't live to confirm it. Perhaps the psychologically satisfying form of detection lies not in prediction, but in ongoing verification that no change has occurred. Each morning, physicists power MRI magnets, satellite gyroscopes, and laser interferometers, all dependent on constants that have to remain constant. The persistence of functionality is an empirical statement. Vacuum decay has not yet started. The endless repetition of successful experiments, the beam aligning, the resonance matching, the photon frequencies agreeing, is itself detection by absence. Every functioning device on Earth is an alarm clock perpetually ringing with silence. In philosophical literature, some call this the principle of continuing evidence. Instead of seeking to predict collapse, we interpret the survival of regularity as data confirming persistence. If at some point correlations between independent physical constants failed catastrophically, if Planck's constant measured differently in one lab than another without environmental cause. We could infer the vacuum had regionally changed. But such differential results can't exist under light-speed expansion. Conversion would engulf all observers equally. Therefore, constant coherence everywhere is the only possible signal until the final one: none. Still, discussions of impossible detection yield metaphors worth keeping. The universe's metastability becomes a lesson in epistemology. Knowing has limits built into what can be known. Perfect foreknowledge would require signals faster than the event itself, the single rule even omnipotent mathematics forbids. In everyday life, we live comfortably under the same constraint. We rarely know the instant before sleep, the exact moment a neuron fires or a raindrop fractures. Vacuum decay is that constraint elevated to cosmic scale. Interestingly, the search for precursors tangentially illuminates unrelated mysteries: the nature of dark energy, the accuracy of time standards, and the topology of quantum fields. While chasing the undetectable, physicists invented technologies like optical lattice clocks and femtosecond interferometers. Their instruments now test general relativity with precision surpassing Einstein's imagination. In an ironic twist, our fear of the universe's demise improves our ability to understand its life. From this broader view, detection possibilities transform from paranoia into celebration. They remind us how much our species desires participation in knowledge, even when that knowledge includes our own limits. Every satellite alignment, every null result coalesces into a hymn to continuity. For the physicist tuning an interferometer at midnight, each moment of stable laser phase is confirmation that the fabric of space still hums by the rules she knows. Until it doesn't, and even then, she'll never know that she's been proven wrong. And so the question, could we know, becomes a koan. The attempt to answer generates understanding even if the answer is no. In striving to foresee the unforeseeable, we refine our definitions of observation, causality, and existence itself. Detection in this context means appreciation, seeing that the world functions in perfect delicacy according to principles we can measure today. That recognition offers more peace than any warning ever could. The next tick of a clock, the next photon striking your skin, the next breath taken all serve as cosmic confirmations of survival. The vacuum holds. That for now is all the detection we'll ever need. Escape routes? Multiverse theory. From one perspective, the notion of a true vacuum that annihilates its parent universe sounds like ultimate finality. Yet physics, with its habit of expanding every boundary, substitutes endings with context. When theorists examine the vacuum landscape implied by quantum field theory and string theory, they uncover not one potential minimum, but an ocean of them. A vast array of physically self-consistent configurations scattered across an unimaginable, multi-dimensional space of possibilities. The result is what cosmologists cautiously call the multiverse. Each region corresponds to a different vacuum, a different version of physical law. In such a framework, vacuum decay no longer reads as extinction, but as migration, the universe moving from one coordinate in that landscape to another. To picture this multiverse landscape, imagine a range of mountains frozen in twilight, every valley representing a stable or metastable vacuum. The Higgs field is a climber resting in one valley, safe for now, but overlooking countless others that descend deeper. Each descent corresponds to a distinct combination of constants, different ratios of forces, different particle masses, different dimensional shapes folded into space-time itself. In this geography, our universe is simply one basin among innumerable others. When physicists run the equations of inflation, especially eternal inflation, they discover that once the process begins, it almost never ends. Space keeps inflating somewhere, while local pockets fall out of the inflationary phase to become distinct universes. Each pocket occupies its own vacuum and evolves independently. Eternal inflation supplies a natural mechanism for perpetual creation. In the earliest fractions of a second after the Big Bang, the cosmos expanded exponentially, driven by vacuum energy. In most regions, that expansion subsides, producing ordinary space like ours. In other regions, it continues forever, spawning infinite bubbles of new universes. Mathematically, inflation behaves like decay in reverse, a constant tunneling out of the high-energy vacuum into successively lower ones. The multiverse then becomes a kind of cosmic foam, every bubble its own space-time domain. Vacuum decay merely continues that eternal process within mature universes. Our bubble may one day tunnel again, creating a descendant cosmos beyond our comprehension. This picture reframes the existential anxiety. The disappearance of our particular laws would not erase reality, it would shift it. From the multiversal viewpoint, each decay event acts as reproduction. The parent universe yields energy to generate a daughter domain with altered parameters. What looks to internal observers like annihilation looks to the global topology like evolution. Some research groups at Stanford, Cambridge, and Tokyo even represent this mathematically using Markov chains, probabilities of transitions between vacua as paths through a network. One node goes dark as another lights up. Conservation of total existence still holds, but the local script changes. The multiverse model also eases one of the long-standing puzzles in physics, the extreme fine-tuning of constants that make life possible. If there are countless vacua with varying properties, it's unsurprising that at least one possesses the delicate balance we inhabit. That reasoning is the anthropic principle in its statistical form. Observers arise only in universes compatible with their existence. Our metastable valley need not be unique or deliberately designed. It is simply one of the few capable of supporting structures long enough for curiosity to emerge. In this sense, the very instability that might one day end us also explains why we exist at all. Only metastable universes linger. But the multiverse hypothesis raises another question. Could a vacuum decay be contained, limited to a single domain, rather than spreading without bound? Traditional descriptions suggest the bubble of true vacuum expands until the entire false domain is consumed. Yet if space itself is still inflating globally, the expansion of the parent medium may outrun the bubble's growth. In that case, isolated decay events produce finite pockets that never merge, each sealed off by the continuing inflation of the external space. The overall ensemble endures, an infinite matrix of self-contained universes, some young, some ancient, some newly reborn from others' endings. This possibility introduces an unexpected escape route. Not for us, physically, we cannot cross between domains, but for existence in general. No matter how many individual bubbles collapse, the total multiverse persists. Something always survives somewhere. When a cosmologist says the end of the universe, they increasingly mean the end of our branch. The process resembles biological evolution scaled to the cosmos. Variations arise, some stable, some short-lived, but life. The abstract process of physics itself continues through diversity. Theorists model this using the so-called string landscape. String theory, despite its controversies, provides a framework capable of hosting an enormous number of vacua, perhaps 10^500 or more. Each arises from different ways of compactifying the theory's extraspatial dimensions, different twists and folds of invisible geometry. Every configuration yields distinct low-energy physics. The multiplication of vacua once seemed an embarrassment, a lack of predictive power, but under the lens of vacuum decay, it becomes the feature that ensures continuity. Our Higgs field may one day roll or tunnel into a configuration corresponding to a completely different compactification. What emerges could be another universe, governed by forces unfamiliar but mathematically consistent. Within this cosmic ecology, vacuum decay events resemble seeds germinating. The false vacuum functions like fertile soil, an energetic state continually producing new shoots of reality. Each sprout expands until isolated by inflation's relentless growth, developing into an independent cosmos with its own arrow of time. Observers inside any one bubble perceive a single coherent history, yet from the larger perspective beyond all bubbles, history forms a branching tree without root or trunk. The boundary between destruction and creation blurs until the terms lose meaning. A question inevitably follows. Can physics ever verify the multiverse? Direct observation seems impossible. Every domain is causally sealed. Still, researchers hunt for indirect clues. One proposed signature involves bubble collisions. If two universes formed close enough during the early inflationary phase, their expanding fronts might have intersected, leaving imprint circular scars in the cosmic microwave background. Teams analyzing Planck's satellite data have searched for such patterns. A few statistical anomalies sparked intrigue, none definitive. Another hint could come from gravitational waves left by ancient vacuum transitions, faint ripples in spacetime that permeate the cosmos. If instruments like LISA or pulsar timing arrays detect a background not attributable to known astrophysical sources, it might be the chorus of neighboring universes singing faintly through the void. Mathematics offers stronger evidence than observation. When cosmologists apply quantum mechanics to gravity, they find that the potential energy governing inflation has no true minimum. It's a rolling landscape with plateaus. Probabilities never reach zero. Even if a universe cools into apparent stability, fluctuations at the Planck scale can re-inflate small regions. In other words, once creation starts, it never globally ends. That prediction, derived independently by several researchers, unites inflation, vacuum decay, and the multiverse into one continuous mechanism. The cosmos doesn't need a metaphysical motive. It's simply exploring its own mathematical terrain forever. Still, skepticism remains healthy. Critics argue that without observable consequence, multiverse talk risks stepping outside empirical science. They remind us that beauty of theory is not evidence. Yet even skeptics acknowledge the explanatory symmetry. The same equations that yield chaotic unpredictability at micro levels can yield a hierarchy of universes at macro scale. If quantum mechanics allows every potential outcome somewhere in Hilbert space, reality may already embody those outcomes spatially, each within its own patch of vacuum. In practical terms, the multiverse cancels nihilism. If our bubble ends, the grand game continues elsewhere. Energy converts, equations persist. The broader system loses nothing. Some theorists even speculate that information usually considered destroyed in a vacuum transition might encode gravitationally across boundaries. The quantum equivalent of genetic memory, ensuring each new universe inherits subtle patterns from its ancestors. Highly speculative, yes, but consistent with the principle of unitarity that demands total information conservation. Perhaps the constants of successive worlds aren't random. Perhaps they drift gently, evolution guided by feedback written in geometry. Philosophers latch onto this image. If the multiverse truly exists, then apocalypse loses its monopoly on finality. Our demise becomes a local event in a never-ending symphony. Consciousness might vanish here, yet re-emerge wherever similar conditions arise, not by transfer but by recurrence. The thought that awareness could reappear, not as memory but as structure, colonizes the imagination with calm. The sea remains, waves differ. Interestingly, mathematical treatments of eternal inflation predict that most regions in the multiverse inhabit a perpetual balance between decay and expansion. At any given time, some bubbles collapse, others form. The percentage of space still inflating always dominates, meaning the overall volume of existence grows without limit, even as individual universes perish. In this statistics-driven immortality, everything transient contributes to the eternal. Vacuum decay, then, is not a cosmic tragedy, but a cosmological metabolism, the universe exhaling and inhaling structure. Yet the idea of countless unreachable worlds unsettles intuition. How can something that cannot be observed hold meaning? The physicist's answer is consistency. The multiverse explains patterns we can observe, why constants lie just where they must, why inflation lasted as long as required, why quantum probabilities remain normalized. It's akin to deducing unseen planets from their gravitational tugs. We may never view another bubble directly, but the balance of equations demands their existence the way Mercury's orbit demanded Einstein's relativity. If this interpretation holds, the immediate dread of vacuum decay softens. Our universe could collapse tonight and still be part of a thriving ensemble. On cosmic scales, we'd scarcely count as a heartbeat, yet our fleeting existence would have altered the probabilistic landscape, however minimally. Through that participation, every observer adds to the multiverse's diversity of experience, even if none survives to remember. At the intersection of physics and philosophy, another idea arises. Maybe we're already inside the product of countless prior decays. Each successive universe refines parameters, trending toward conditions favorable for complexity. In models of cosmic natural selection, universes that produce black holes spawn offspring through internal vacuum transitions near singularities. Those offspring inherit physical constants slightly mutated by their progenitors' traits. Over unthinkable epochs, universes with laws congenial to longevity proliferate, the multiverse's version of evolution by selection. Our metastable parameters, balanced between safety and change, might represent the result of that process. Even within this speculative grandeur, limitations remain. No communication can cross boundaries. Information channels terminate at bubble walls moving at light speed. For any being inside one bubble, the outside multiverse is abstraction. Nevertheless, theoretical physicists treat its presence as boundary condition. In quantum cosmology's wave function of the universe, the probability amplitude extends over all possible configurations. The wave doesn't end at our vacuum, it integrates over every minimum. The multiverse is therefore not optional, it's built into the mathematics of existence itself, regardless of observational reach. From the human perspective, this realization shifts emotion from fear to belonging. Our universe joins an infinite lineage, each transformation a continuation of the same creative principle. If metastability grants the possibility of change, multiversal continuity ensures that change is never absolute loss. The Higgs field's potential isn't a trap, it's a stairway of energy levels, each step a new cosmos. We occupy one rung for now, secure yet temporary, as countless others ascend and descend around us in the grand staircase of creation. The ethics of knowledge also expand. Knowing our cosmos may be one cell in a perpetual organism encourages humility over dominance. Whatever we build, whether cities or theories, rests within broader processes indifferent to individuality, yet rich with continuity. The awareness that decay elsewhere births creation reframes scientific curiosity. We study metastability not to avert the inevitable, but to join the dialogue, to understand our place within an infinite system constantly rewriting itself.